Hello everyone, today we are talking about transmission-aware allocation of bandwidth variable transceivers in DWDM optical networks and the effect of regenerator placement on spectrum utilization and system throughput. First of all, I'd like to thank the other authors of the work for the fruitful discussions and great assistance. We'll start with a brief overview of the problem, then we quickly run through constraints and objective functions. After algorithm workflow, we will look at the simulation results, and eventually we will summarize our achievements and we will look at the open issues that might be addressed in the future. In modern optical networks with constant traffic growth, it is essential to configure light passes for a given traffic demand in optimal way. That is, to allocate proper bandwidth variable transceiver configurations to provide feasible quality of service. In other words, bitrate and modulation format should be selected on transmit side in such a way that transceiver bitrate covers requested traffic and the signal at receive side meets receiver parameters, for example, receiver sensitivity with respect to OSNL. Selecting transceiver configuration with respect to quality of service, we define bandwidth of a light path, and in other words, spectrum utilization. Having multiple traffic demands in a network, intuitively we should allocate light passes as close to each other as possible. At this moment, the nonlinear interactions of light passes or optical channels within fiber comes into play. And one more difficulty appears. We cannot estimate nonlinear noise more or less accurately until we know transceiver configurations for all traffic demands in the network. For example, at the beginning, we do not know will there be 2 or 3 transceivers used to realize either traffic demand number 1 or number 2. Another thing that should be kept in mind is a scalar of optical network. Long light passes leads to a significant OSNI degradation, even due to ASC. There is a nonlinear interference on top of it, so it's quite difficult to meet receiver limits without signal regeneration. As a result, we come to a question: how to allocate transceivers and to account for requested traffic, transceiver, and route parameters in order to meet receiver limits. For instance, how to calculate nonlinear noise for a given light path with different neighboring light passes in different fibers along the route, until all light passes are configured. It would be good also to avoid an iterative approach to accelerate the process in order to reuse the algorithm as for offline planning when a network is designed and configuration of equipment is defined, so maybe for online planning. Now, let's formulate some constraints. First of all, we need good quality of service, that is, we need to meet receiver limits. We are targeting a receiver OSNL threshold because required power level can be almost always achieved by adding more amplifiers. We calculate OSNL degradation caused by 2 things, ASC and nonlinear noise. In other words, we compare receiver threshold with generalized SNR. Next thing is requested traffic, that is, transceiver bitrate should be greater than bitrate of a traffic demand. To finalize light path configuration, we use flex grid and consider allocation of frequencies in C-band or in C+L bands. In our simulation, we use bandwidth variable transceiver configurations with different modulation formats and bitrates in range from 100 gig to 600 gig. As regards regenerator placement, we do not focus on its optimization with respect to transceiver number or bandwidth minimization. We just use simple heuristic controlled by 2 parameters. We will look at the algorithm a bit later. So in this work, we use regeneration just to reduce OSNI degradation caused by long routes, for example, due to amplifier noise. And we do some assumptions. The input for the algorithm is physical topology of the network. That is, all we know is fiber loss and length. There is no information about a drop equipment configuration. That is, no information about WSS loss and amplifier parameters. So we assume WSS penalty, amplifier noise figure, and calculate ASC, assuming exact span loss compensation. That is, we use variable gain amplifiers. As it was mentioned, until all light passes are configured, frequencies are not known, so at nonlinear noise estimation, we allocate light passes for a current routed traffic demand and adjacent traffic demand within each link of a current route around center of a C-band. As we assume frequencies, we do not account for wavelength-dependent amplifier gain and fiber loss. Having defined constraints and assumptions, we are minimizing total bandwidth of all bandwidth variable transceivers allocated to a current traffic demand. Afterwards, we can minimize overall spectrum utilization in a network through the appropriate allocation of transceiver frequencies. We developed our algorithm in a frame of network design environment, where transceiver allocation algorithm is one of the steps of the network design process, which goes from network topology definition to frequency allocation, equipment configuration, and performance assessment. Now, it's time to have a look at the different steps of transceiver allocation algorithm. We can see the different set of traffic demands, in other words, traffic demand metrics, at each step of multi-period planning as an input for the algorithm, along with parameters of a network topology. At each period of planning, the structure of traffic demand metrics is not changed. Only requested traffic or bitrate of each traffic demand varies. So we do some pre-calculations once for all period of planning in order to reduce simulation time. Those are routing and optionally regenerator placement. The routing is done through the use of the extra algorithm, which minimizes route length. Afterwards, regenerator placement can be done. In other words, for each period of planning, we consider two scenarios of transceiver allocation, with and without regenerator placement. In the scenario with regenerator placement, the route, with parameters exceeding maximum length and maximum number of spans in a route, is replaced by a set of routed demands of shorter length. These new routed traffic demands meet the constraints. After adding regenerator points, new routed traffic demands may have the same route as another routed traffic demands in the network. So, the grouping is done, and some routed traffic demands of the lower requested traffic and with the same route are replaced by a new routed traffic demand which has the same route and higher requested traffic. And the last thing which is calculated in advance is route-specific OSNA degradation caused by ASE. Then, the multi-period planning starts. We consider a year as a period of planning. The algorithm starts calculating GSNA for each routed traffic demand within a year-specific traffic demand matrix. At first, the list of available configurations of bandwidth variable transceiver is filtered with respect to route-specific OSNA. Then minimal and maximal channel placement is calculated for a current traffic demand and all traffic demands which share any link within current route. And nonlinear noise is calculated with the assumptions about wavelengths for the lower and upper number of channels. List of transceivers is again filtered, now with respect to the lowest value of GSNA calculated at previous step. And the valid combinations of transceivers are built. The total bandwidth of transceiver combinations should be minimal and their total bitrate should not be lower than the requested bitrate of the routed traffic demand being processed at this step. For example, for 600 gig traffic demands, valid combinations might be 1 600 gig channel or 3 200 gig channels, and so on. Then, transceiver combinations with the lower total bit bandwidth is selected. When all routed traffic demands have been processed, frequencies are allocated and the transceiver allocation is done for a given period of the planning. Then the steps, starting from the year-specific traffic demand matrix selection to frequency allocations, are repeated for all remaining periods of planning. And now we go to simulation results. At first, we check the feasibility of our nonlinear noise calculation through the comparison with the result published earlier. We simulated 6 100 gig channels passing through 2000 km transmission line within our network design environment, which uses the same approach to nonlinear noise calculation as the algorithm we present here. In the reference paper, for the given transmission line, the values of OSNA and GSNA are measured and simulated. Unfortunately, we have no experimental data, but our simulation data are in good agreement with the values reported in the paper. To test the speed of the algorithm, we did simulation for several networks with with different number of add-drop nodes, links, and different traffic demand matrices. We did simulations of 6-year planning for 14 and 50 node subnetworks of German network, and 10-year planning for 17 node subnetwork of German network. These topologies have fiber spans of different lengths. That is why we use incoherent EGN model for nonlinear noise calculations. For all topologies, 2 scenarios with and without regenerator placement were simulated. Here is the table with simulation type for different combinations of physical topology and traffic demand matrix. In our simulation, traffic demand matrix is built on an assumption that every node in network talks to the others. That is why number of traffic demands in 15-node network is much higher than in networks with 14 or 17 nodes. And the simulation time also varies. Just a small note, if the number of traffic demands in 15-node network is reduced, say 6 times, the simulation times become comparable. Another thing that was compared is minimal GSNR margin. We compared 2 values. First one is the target margin of 1 dB, which is used at transceiver allocations, and another one which is calculated after complete configuration of all equipment, including WSS ROADMs and amplifiers with the network design environment. Calculated margin is in a good agreement with the requested one. Now, let's run through simulation results obtained for 17-node network. Here we compare our results with another reference paper, where this network was used to model 10-year planning. As we can see from the picture, the solutions generated by our algorithm are closer to the requested system throughput, at least in the early planning years. Depending on network configuration, that is, depending on topology parameters and requested traffic, the solutions with the regeneration points can provide better spectrum utilization in comparison to solutions without regeneration placement. Another interesting point is the usage of regenerators allows to utilize only C-band for the whole 10-year planning, while the solution without regenerators and the solutions produced by the reference algorithm require a wider spectrum range, at least for the last year. Here is the relative difference of our algorithm and the algorithm reported in the reference paper. As it was mentioned above, our algorithm generates solutions with better spectrum utilization and system throughput at the early years of the planning. On the other hand, starting from the 6th year, the solutions are better in terms of transceiver count. And the last picture I'd like to show here is the relative difference of the solutions generated by the algorithm for the scenarios with and without regenerator placement. The scenario with regenerator placement gives the solution with better spectrum utilization and for certain combinations of topology parameters and requested traffic with a lower transceiver count. And this brings us back to the question of regenerator placement optimization during the transceiver allocation, which is for now out of scope of this work. And the last but not least, summary. We have presented transceiver allocation workflow, which accounts for as linear so non-linear degradation of a signal through the calculation of generalized SNR. The usage of regenerators allows to improve spectrum utilization, to better control system throughput, and to reduce number of transceivers, at least for some network configurations. Of course, we didn't address everything we would like to in this work. So in the future, the algorithm can be extended at least in order to account for optimization of regenerator placement, frequency dependence of network parameters such as fiber loss and amplifier gain. And I believe the algorithm can also be accelerated. This will allow us to reduce it at online planning. Thank you very much. Now it's time for questions and comments.